about momentum and forces now that we had some exposure to the impulse momentum theorem. So what we're first going to be talking about is internal versus external forces. And what we have here is a table that's shown by this rectangle here. And then we have a side view of this table as well, shown like right here. And what I'm going to do is put these two pucks on the table, one blue one and one red one over here, and have them go into motion. Okay, so they eventually hit with each other. The blue one was originally moving to the right, and then the red one was moving upward. And the resulting forces look something like this. You got a force that's going a diagonal this way on the blue one, and they have a force on a diagonal that's going this way. But if you pay careful attention, you'll see that these two forces add up to be 0. And we'll see in a moment that these are actually called internal forces for that reason. Now, if we continue the motion, we'll see we get something like this. And then you might see that maybe one of the pucks might fall at the table like this. And what you expect to see is that there would be a gravitational force that's acting on this red puck, which causes this red puck to fall downward. We call this an external force because this is going to give a net force of non-zero on this two-puck system, and it's going to affect the red puck. If we continue motion, this is what we get. So the red puck falls to the floor. Now let's take a look at momentums and forces. So we have already experienced the impulse momentum theorem, and hopefully we all know that this is what this impulse momentum theorem is going to be written as. But a new thing that we want to keep in mind here is we actually want to deal with more than one momentum vector at a time. And the way we represent this is by means of this relationship here. This summation represents taking more than one momentum vector, represented by this. So we have pi summed from I is equal to 1 up to n. So what does this mean? If I say that n is equal to 2, that can represent these two pucks over here. I have one puck here, and then another puck here. Let's say I call this red puck 1, and this blue puck 2. Those two pucks are going to be represented for this summation here. So the momentums are going to be captured for the summation. And then you get the total momentum. So this is effectively just saying that the total momentum P, capital P that is equal to P1 plus P2. And then we also know that the net force can be represented as the mass times acceleration. That's Newton's second law. But we also derived from last class that force can be represented as the derivative of momentum with respect to time. So there are your definitions for total momentum and Newton's second law in terms of momentum. And if we put things together, let's not just stop at saying that we have just a singular force that is acting on a singular particle. Let us actually combine this force relationship here with this momentum relationship here. And what we find is that we get a summation over all these forces, and that is also going to be equal to the summation of the derivative of momentum with respect to time, and that altogether is going to be equal to the derivative of the total momentum with respect to time. And that's how we represent the sum of our forces as change in total momentum. And then if we take a look at this little demonstration over here, we got two blocks, or carts if you will, one red and then one blue. And I'm going to represent their momentum by this. So we got a red vector here, and hopefully you're familiar with the momentum relationship. That's mass times velocity. So momentum 1 and then momentum 2 over here. Now let's set these carts into motion until they eventually collide. Okay? They collided, and what you might expect is that you'd see a new velocity, or in other words, a new momentum. And that's represented by P prime, which is going to be equal to the sum of the masses, because, well, these two carts are now connected, times a new velocity, V prime. And if we keep having the carts go into motion, they'll just keep going until maybe they hit, like, say, a wall or something like that. And what we gather here is that the new momentum, P prime that is, of the combined cart system should be equal to the sum of the momentums of the individual carts. That's P1 and P2. And if we want to sum things up, we see that internal forces occur at collisions, just like we saw here over at this table over here with the blue puck and the red puck, and they tend to conserve total momentum. And that's what we can see over here in this box like this. When the two carts collided, they had internal forces between each other, which caused them to have a new momentum. And then external forces, such as gravity, so like what you saw with this red puck falling off the table, and you can see that it resulted in the puck falling onto the ground, or maybe impact with a wall, like you saw here with these two carts colliding with this wall, eventually just changes the total momentum. Okay, so now let's take a look at our conservation of momentum in 2 dimensions through a bit more of a mathematical lens. And I will refer back to this 2 pucks on a table example over here. So let's bring the pucks in. What we have here is we have our 2 pucks, of course, and what I'm going to want to do is I'm going to want to model the momentum for each of these pucks. So the momentum for my blue puck and my red puck are going to be represented by these equations here. My blue puck is going to be moving in the x direction, so I represent this as P2. 2 is going to represent blue, x for x direction, and that is equal to m2, being the mass of the puck, times v2x. That's whatever the speed or velocity of this blue puck is going to be initially. And then the same idea applies also to here, where we have P1 representing our red puck, and then we have y for the direction that the puck is moving, being, well, the y direction. And that is equal to m1 times v1y. So if we take a look at the motion, let's see what happens. Okay, they eventually collide, and we know there's internal forces at play here. That's going to cause the motion to change a bit. And let's see what the new motion is going to be. So they're going to be moving in different directions now. So the blue puck is going to want to move upward, and then this red puck is going to want to move this way. And what we see here is that our new momentums become this, where we have P prime for the new state, that is, and I have 2y this time for my blue puck, because while it's going to be eventually moving in the y direction, that's what I'm assuming here, and that is equal to m2, the mass doesn't change, times v prime 2y. So we're dealing with potentially a new speed as well. And then we have something similar that happens when we're talking about the red puck, where we have p prime 1x, so x representing, well, of course, the x direction, and then we have the prime for new momentum. And then same mass, and then times our new velocity. And then also something that's also good to keep in mind is you might notice that the velocity of the center mass is going to be constant. So just kind of keep that in mind. That's something that we are going to take a little bit of a look a bit later at, and actually prove that that is true. And if I continue the motion, let's see what we get. Okay, so that's just a freeze frame of the motion. And I'm going to leave it at that motion right now, okay? Now, we are going to take a look at the momentum conservation. in a bit more of, again, a mathematical lens. What we have here in the x direction is that we have that the momentum before is equal to the momentum after, for particularly the x direction, that is. And the way we do this is that we set the components, the x components that is, equal to each other. So what we'll say is that the momentum of, like, say, 2x, because that's the only momentum that's involved in the x direction in the before case, is going to be equal to the momentum in the final case, which is p prime 1x. And if you take a look at this chart over here, it might make a little bit more sense. So we have this here is equal to this, because these involve x. And if we put the right-hand side of the equation together, we'll get this relationship right here for x direction. And then we could do the same thing for the y direction as well. So we have y, the before and after are the same in the y direction. And then if we look over here, we'll see that this is going to be equal to this. And thus, we get this equation right here. Now, you may be thinking to yourself, right, what if maybe these pucks are going like on a diagonal or something like that? Well, let's take a look at the general conservation of momentum in this case. So, it's the same idea. We have px before is equal to px after. But the thing is, the way we actually take a look at conservation of momentum, if like we're talking about these pucks moving diagonally rather than just along the x or y direction, we get this whole equation here. We'll get the mass of one puck times its velocity in the x direction plus the mass of the other puck times the velocity in its x direction is equal to the mass of the puck times its new velocity in the x direction after collision, and then plus the mass of the other block times the velocity in the x direction, well, after the collision as well. So you work component-wise when it comes to these diagonal directions. And the same thing applies to the y direction as well. So you have y before is equal to y after, and then you'll get pretty much the same thing, except that you're just working with the y direction this time. So now that we have established this information over here, that we know that we can conserve momentum in the x and y directions, let's sum things up. So we can see clearly momentum is going to be conserved in the x and y directions separately. That is going to be the rule that occurs when we have only internal forces at play. And then also we'll see that the total momentum is going to be essentially the same before and after the collisions. Now that we talked about momentum and also conservation of momentum, we're now ready to move on to center of mass and velocity. And naturally, we'll start by talking about what center of mass is. So let's refer back to our, rectangular space here. And then we also have this red mass over here. And I'll mention what this 4 times means very soon. And my goal is to figure out the center of mass between this red mass and then also this blue mass over here. And I'm going to be assuming that this red mass has 4 times the amount of mass as this blue mass over here. And the goal of center mass, or a good way of actually thinking about what center mass is to imagine if these two masses, this mass and then this mass, were connected by some straight line like this. And my goal is that I wanted to balance these two masses in the air by means of putting my finger somewhere in between those two masses. So that position where my finger would be placed is going to be represented by this X here. And if you were to work out the details, you would find that you can actually figure out the distance from this x to the blue mass and the distance from this x to the red mass is going to be related by this relationship down here. And let's actually interpret what that relationship means. According to this relationship, we see that the mass and distance are going to be inversely proportional to each other. That is for two masses only. Things get a little bit more complicated when you're talking about 3 or more masses. So what does this mean? If I look at this relationship quite carefully here, I'll see that for a bigger mass, let's say, for instance, that the red mass is the bigger one, of course, and I'll call this M1, I can see that M1 is going to be bigger than M2 being the blue mass. So that means my ratio is going to be 4 to 1, which then, if I look at the relationship between D2 and D1, that is going to be the distance. So D2 is going to be the distance between the blue mass and then to this X here, while D1 is going to be the distance from this red mass to this X here. And since we know M1 over M2 is 4, then we know D2 over D1 must be 4 as well. So the D2 must be larger, and I define that as the distance from the blue mass to X. So this distance here, from here to here, must be larger, 4 times larger that is, than the distance from here to here. And if I were to actually place my laser, if you will, somewhere on this diagram to actually represent this ratio, my laser would probably be somewhere like maybe like right around here. So if I place my finger right around here, then the two masses would then be balanced. So, how do we actually figure out the center of mass? Well, of course, most of the time in physics, we like to use equations. So one important parameter that we need to define is the total mass, which is going to be represented by this equation here. And just like the way we were talking about momentum with summation notation, the total mass, m, is going to be equal to m1 plus m2. And then we're going to be applying similar summation notation to x center mass. That's what COM stands for. And then what we can see here is that the way we can represent our center mass in the x direction, that is going to be taking the sum of the product of each of the masses times their distance. Okay? And then that's going to be divided by 1 over the total mass. And to put this into a more concise equation, we get this over here, where essentially your center mass just turns out to be just like a weighted sum. Where you can see you're taking a sum of some products divided by the sum of masses. And then you have the y center mass, which is then going to be equal to 1 over m. And then you're going to do likewise the same type of methodology here, where you're going to be taking your product of your mass times your distances. And that is going to be equal to another weighted sum as well. And we'll go over an example just to make these parameters a little bit more concrete, because right now these parameters might seem to be a little bit abstract. So just keep that in mind. And then we have center of velocity. Now I want to bring this up because this proves something that I was talking about on the previous slide. So we can see that the velocity to center mass is going to be equal to the derivative of our center mass, that is going to be the position of the center mass with respect to time. And that is going to be equal to 1 over total mass times the summation of our mass times the derivative of the position of our masses divided by, with respect to time. And then what we can see here is that we see that this dr dt turns out to become a velocity. And that velocity is shown right here in this equation. And if you look underneath the summation here, you'll see that this mass times velocity clearly becomes our momentum over here. And if we keep going forward, we'll see that our velocity of center mass is, of course, equal to this. So this is a carbon copy. But if you look very closely, if you look right here at this equation here, or the summation, I should say, you'll see that this turns out to be something familiar. You'll see that this here actually turns out to be our total momentum. And rewriting this, we find our velocity of center mass turns out to be our total momentum over our total mass. And to put this in a more familiar form, we see that total momentum is equal to total mass times the velocity of center mass. Interesting. And why is this important? If we think about this, if we have a conserved momentum, that means our total momentum vector does not change. That means that P, capital P that is, does not change, and mass, total mass that is, does not change, then that means that also the velocity of center mass must also not change. And just to kind of sum up what I said, total momentum being conserved, that means that the total momentum does not change with time. The velocity of center mass will also be conserved. Now let's try to make a bit more sense of those center mass equations that I talked about on the previous slide, where we were talking about those weighted sums and all that. So let's take a look at a concrete example regarding that. So what we have here is we have two masses, one red square over here that has a mass of 4 kilograms, and it's situated at this point here in space. Its x-coordinate is going to be 2, and its y-coordinate is going to be 6. And then we have this blue ball right here where its x-coordinate is going to be 8, and then its y-coordinate is going to be 2, and it has a mass of 2 kilograms. And we expect that the center of mass would be situated a bit closer to the larger mass that is. So that agrees with what we saw in the previous slide. And then here are equations that we saw from the previous slide as well. And right now, they might just seem to be kind of a mismatch of like a whole bunch of different variables. But let's take a look and see how we actually use them. So what we have here is we have x center mass is going to be equal to 1 over 4 plus 2. Where does this 4 plus 2 come from? It comes from the sum of these two masses here. 4 kilograms plus 2 kilograms. Okay? So that's where our mass come into play. But then we have this stuff over here. What are we going to do here? What we do is we are essentially going to be wanting to take a look at this part of our summation, or equivalently, you could take a look at this part here. And what you do is you take one of the masses, 4 in this case, so 4 is over here, that's the red one, and then we take the x-coordinate, or the distance on the x-axis from the origin, we get 2. So that's going to be 2 here, so 4 times 2. That is going to represent our red mass. And then, if you take a look at the blue mass, you get 2 kilograms here. So go over here, find your distance from the origin to the point on the x-axis where your blue mass is located. So that is going to be 8. And then you get 2 times 8. Do the math out, you'll get 4. And then the process for the center mass in the y direction is very similar. You'll see that for the y direction and involving the mass, you'll get the same parameter here, where you get 1 over 4 plus 2 is going to be the same as this one up here. And then things get a little bit different when you're looking on the inside here. What you have is that you have 4 again for this red mass, and you want to take the y-coordinate this time, so you get 6. Okay, so that's 4 times 6, and that's what we get over here. And then we have our other mass here, so our blue one, 2 kilograms once more, and that's going to correspond to a y-coordinate of 2. So 2 times 2, do the math all out, you get 4, and then 2/3. 4 and 2/3, that is, written as a mixed number. And that kind of agrees very closely with our estimation here. We can see that the center mass is going to be closer to the red mass. And if you just kind of want to refer back to the equation I was talking about a little bit earlier, here it is. You can actually kind of confirm it yourself if you want to work out the details and the geometry. That's a good exercise for you to do. But keep in mind, center mass is going to be closer to the larger mass, and that agrees with our inverse proportionality, which is pretty nice. And here's just something to kind of think about. If these two masses started moving with constant velocity, what would happen to the velocity of the center mass? So, if we think about this, right, we'll see that the total momentum will be conserved, and we'll see that the velocity of the center mass will remain constant. And this velocity of center mass will remain constant whether or not these two masses collide or not. And this is something that's very important for one of your questions inside the activity as well.